Swayam Prabha. Digital India. Educated India.
The next remark, all these remarks can be proved, but I am just giving as a remark, it is for the understanding. The next remark, let x be a continuous type random variable. Let x be a continuous type random variable with CDF capital F of x. Okay. If the expectation x exists, that means the provided condition is satisfied, then you can always find the value of expectation of x, that is E of x, that is a integration 0 to infinity 1 minus f of x dx minus infinity to 0 f of x dx. This is a very important result. Whenever you have a continuous type random variable with the CDF capital F of x and the expectation exists, then you can always find the value with the help of CDF. You do not need the probability density function of that continuous type random variable. From the definition of expectation, when x is a continuous type random variable, if you know the probability density function, if the expectation exists, then E of x is same as minus infinity to infinity x times f of x dx, where that small f of x, that is a probability density function. But now what I am saying is you do not need a probability density function. With the help of CDF itself, you can able to find the expectation provided it exists. Let me give one nice pictorial representation of how to compute the expectation for this when x is a continuous type random variable. Recall, when x is a continuous type random variable, the CDF is the continuous function in the whole real line from minus infinity to infinity. When x is a continuous type random variable, the CDF of the continuous type random variable is a continuous function in the whole real line minus infinity to plus infinity. Therefore, I am just making a one CDF, it asymptotically touches 1 at infinity. So, this is the CDF of some continuous type random variable. Okay. 0 to infinity 1 minus f of x dx, that is same as area below 1 till f of x between the interval 0 to infinity. So, you can shade. So, this quantity, the shaded quantity, is nothing but the 0 to infinity of 1 minus f of x dx. 1 is a line, f of x, 1 minus f of x, 0 to infinity, that is the area between the f of x with the line 1, that shaded area is 0 to infinity 1 minus f of x dx. Next integration minus infinity to 0 f of x dx. that means this part. So, whenever the expectation exists for a continuous type random variable, this sign is with the plus sign, this sign is with the negative sign. So, that area plus sign area minus that minus sign area, that value is going to be the expectation value. Therefore, the expectation can be negative or positive based on the area between minus infinity to 0, that is going to be more than or less than the area between 0 to infinity of 1 minus f of x. Suppose x takes x is a non-negative random variable, that is a probability of x is greater than or equal to 0 is 1, using the first remark. Third remark, sorry. If probability of x is greater than or equal to 0 is 1 and the expectation, if a expectation exists, then the expectation of x is going to be greater than or equal to 0, that you can visualize minus infinity to 0 f of x dx, that quantity is going to be 0 because probability of x is greater than or equal to 0 is 1. Therefore, you will get the positive quantity from the first integration and the second integration values is 0. So, this can be visualized. There is another remark over this remark. I started with the continuous type random variable. You can think of a discrete type random variable also. Suppose it takes only the positive values, then one can make if the expectation exists, then the expectation is the same as in the summation form. Let x be a discrete type random variable with values 0, 1, 2 and so on, with taking values 0, 1, 2 and so on, and e of x exists, then we can find the expectation of x. By the definition, it is k times probability of x equal to k, where k is running from 0 to infinity. By using the previous remark, we can conclude that is same as summation of p of x is greater than k, where k is running from 0 to infinity. By using the previous result, summation k is equal to 0 to infinity, probability of x is greater than k, that is same as k equal to 0 to infinity 1 minus probability of x is less than or equal to k. I want to use a similar logic of 1 minus f of x. So, this is a probability of x is less than or equal to k is nothing but f of random variable x at the point k. So, this is same as e of x is a summation over k is equal to 0 to infinity 1 minus f of x at the point k. So, if you see the previous remarks, when x takes the only the non-negative values, then the second integration vanishes. Therefore, you will get the first one. So, first I give the remarks for the continuous type random variable. For a discrete type random variable, this is going to be expectation of x provided x takes the value 0, 1, 2 and so on. So, this is also very important remarks for the expectation. Now, we will move into the second moment, that is called variance. Let Let me give the definition. Let x be a random variable with expectation of x that you call it as a mu which exists. I am going to give the notation for E of x, that is mu which exists. The second order moment about the mean, that is nothing but variance, is defined as expectation of x minus mu the whole square, that is denoted by variance of x. So, finding the value of expectation of x minus mu whole square, that is going to be called as a variance, that is called a second order moment about the mean. Since we are writing the right hand side expectation of x minus mu whole square, that means the provided the right hand side exists. That means you can treat x minus mu whole square, where mu is expectation of x. So, x minus mu whole square, you can treat it as the function of x, the g of x. So, right hand side is nothing but expectation of g of x, where g of x is x minus mu whole square. You can use the previous result, provided the expectation of g of x exists, then the expected value, that expectation of g of x, where g of x is x minus mu whole square, that is going to call it as a variance of x. So, this second order moment one can define after the existence of the first order moment. If the first order moment does not exist, then one cannot define the second order moment about the mean. So, here I have given the second order moment about the mean. Later I am going to introduce a second order moment about the origin, that is nothing but the expectation of x square by making mu 0, or expectation of x square will be the second order moment about the origin. Similarly, one can define nth order moment about the origin. So, now we will discuss the variance first, then later we will go for the higher order moments. So, the variance of x, that is denoted by VAR of x, that is expectation of x minus mu whole square. So, as I said earlier, you do not need to find out the distribution of x minus mu whole square as long as you know the distribution of x and the expectation of x exists and expectation of x minus mu whole square exists, then the value is going to be expectation of x minus mu whole square is same as variance. You can rewrite the variance of x as, first you have x minus mu whole square, you can expand x minus mu whole square. Therefore, after expansion you will get E of x square minus E of x the whole square. The E of x is same as mu. So, whether you compute expectation of x minus mu whole square, or you find out the expectation of x first, that is mu whole square, then find out second order moment about the origin, that is E of x square, then this difference is going to be the variance of x. Similar to the expectation exists or not, same way for some random variable the variance may not exist even though the first order moment exists. If the first order moment does not exist, you cannot define the second order moment. So, even the first order moment exists, there are some random variable in which the second order moment does not exist, therefore, the variance does not exist. So, we can go for simple examples. The first example, let x be a continuous type random variable with the probability density function f of x, the same example, 2 times e power minus 2x, where x lies between 0 to infinity, 0 otherwise. So, how to compute variance of x for this problem is variance of x is same as expectation of x minus mu the whole square, that is same as integration from minus infinity to infinity x minus mu the whole square f of x dx. In this problem, the mu is same as expectation of x, which we got it already, that is 1 by 2. Therefore, this is going to be minus infinity to 0, the f of x is 0, therefore, you can directly go for 0 to infinity x minus 1 by 2 the whole square, f of x is 2 times e power minus 2x dx. We are not finding the distribution of x minus mu whole square, then we are finding the expectation. No, we are using a expectation of g of x, which I said it in the remark. So, x minus 1 by 2 whole square probability density function, which is greater than 0 between 0 to infinity, therefore, minus infinity to 0 vanishes. So, this is same as 0 to infinity of this. If this quantity is going to be finite, then the existence also taken care. Since x takes non-negative values, you are finding this. If you do the simplification, you can get the value, that is 1 by 4. If you do the simplification of this integration, you will get the value 1 by 4. Therefore, for the random variable which is continuous type, whose probability density function is 2 times e power minus 2x when x lies between 0 to infinity, the mean is going to be 1 by 2 and the variance is 1 by 4. Later we are going to conclude this is going to be exponential distribution with the parameter 2. So, the mean is 1 divided by the parameter and the variance is 1 divided by the square of the parameter. So, here the parameter is 2, therefore, it is 1 divided by 4. Let us go for a few remarks over the variance. The first remark, variance of a constant is 0, whereas the expectation of a constant is a constant. Variance means what is the variation about the mean. So, here the mean of a constant is a constant, therefore, there is no variation about the mean, that is alpha, therefore, the variance is 0. So, intuitively you can say the variance of constant is 0. The second remark, variance of x, if it exists, then that value is always going to be greater than or equal to 0. If the variance exists for a random variable x, then the variance is always greater than or equal to 0. That is, expectation of x minus mu the whole square is always greater than or equal to 0. This you can say by using the remarks on the expectation. You go back when the random variable x, whose probability is p of x is greater than or equal to 0 is 1, then the expectation is going to be greater or equal to 0. With that logic, x minus mu whole square, whose probability is always probability of x minus mu whole square greater or equal to 0 is 1, because it is a non-negative random variable. Therefore, the expectation of x minus mu whole square is always going to be greater or equal to 0, because whether it is a discrete random variable or continuous type random variable, this is nothing but if it is a discrete, it is a summation xi minus mu the whole square, probability of x equal to xi, and the probability mass function is greater or equal to 0. Xi minus mu whole square is a positive quantity. Therefore, if it exists, then the summation is going to be positive. If x is a continuous type random variable, then x minus mu whole square probability density function integration from minus infinity to infinity, again integrand is greater or equal to 0. Therefore, if the expectation exists, if the variance exists, then this quantity is also going to be greater or equal to 0. You can combine the remark number 1 and 2 in the form of third remark. If probability of x takes a value alpha is equal to 1, that means it is a constant. Probability of x takes a value alpha, where alpha is a some number, that is 1, then the mean is same as mean of the random variable is same as the alpha, and the variance of the random variable is going to be 0. That means for a constant random variable, the expectation is same as constant and the variance is going to be 0. And this is a if and only if condition. If the variance is 0, then you can conclude that is a constant random variable. When I say constant random variable, the probability of x takes the value that constant is 1, therefore it is called a constant random variable. Later I am going to discuss in detail. So, here the remark is if the variance is 0, you can conclude the probability of x takes that constant is 1. If constant, then whose expectation is the same and the variance is 0. Now, I can go to the fourth remark. Variance of some constant times x plus b, if the variance exists. If the variance of x exists, that is same as if you do the little calculation, you can prove that is same as a square times variance of x plus variance of constant is 0. Therefore, it is going to be a square times variance of x, whereas expectation of a x plus b, that is a times expectation of x plus b. Here variance of a times x plus b, when variance of x exists, then it is same as a square variance of x, because variance of constant is 0.